Welcome to my channel, Beyond Newton. I'm here to introduce you to this amazing universe of quantum physics. But before we do that, I want you to answer this question. Did you know a particle can be in two places at once? Or that just looking at something can change it? Welcome to the strange world of quantum physics. I make videos about the most mind-blowing concepts in science. Let's start with a quick introduction to quantum physics. If you're going to talk about quantum physics, you have to start with this. You probably learned in grade school that everything is made up of tiny building blocks called atoms. Atoms are so small they ray away, below the scale of being able to measure them with our tools. That's why we need something even tinier called an electron microscope to see them. Now if you keep zooming in on stuff, eventually you get to the tiniest possible thing, a point with no dimensions. The weird thing is that stuff still exists. In fact, all of physics exists at this level. We call this the quantum realm. Now, since the tools we use in everyday life aren't advanced enough to measure what is happening in the quantum realm, we use math to describe it. This is called quantum physics. You might be asking yourself, why do we need quantum physics? Can't we just use classical physics for everything? Well, it turns out we can't. Classical physics works pretty well when you're talking about bigger things like baseballs or planets or people. It describes the motion of big things very accurately, but it totally breaks down when you try to use it to describe the super small like atoms, electrons and photons. There are two classic examples that show how classical physics fails. One is the ultraviolet catastrophe. That's where classical physics predicts that hot objects should emit light. That's concentrated at higher energies, or in other words, shorter wavelengths, higher frequencies. That means that the color of the light emitted from a hot object should shift toward the ultraviolet part of the spectrum. But that's not what happens. The hotter an object gets, the more red it looks. This apparent contradiction was one of the major reasons scientists developed quantum physics. The other example is the photoelectric effect. That's where light shining on a metal plate can knock electrons off the plate. Again, classical physics makes a wrong prediction here. It says that the energy of the electrons knocked off the plate should depend on the intensity of the light, but it doesn't. Instead, it depends on the frequency of the light. These contradictions between classical physics and observations are the reasons scientists had to develop quantum physics. So, now that we know what quantum physics is, let's talk about why it's so weird. We'll explore each of these in upcoming videos, but here's a quick teaser. In the quantum realm, things exist in a state of superposition. A particle can be in two places at once. That's because quantum objects don't have definite properties until they're measured. This also means that quantum objects are connected in a spooky way, called entanglement. And finally, there's the uncertainty principle, which says that we can't know both the position and momentum of a quantum object with perfect accuracy. These ideas might seem completely bizarre, but they're necessary to explain how the universe really works at the most fundamental level. In fact, many of the technologies we rely on today wouldn't be possible without quantum physics. Computers, lasers, GPS and MRI machines, to name just a few. So quantum physics isn't just some esoteric theory. It's a powerful description of nature that helps us understand and control the world around us. This is a channel about the most mind-blowing concepts in science. On this channel, we'll break down quantum physics from the tiniest building blocks to the biggest questions of the universe. So if you've ever wondered how reality really works, or what the weirdest parts of the universe are, hit subscribe and join the journey into quantum physics. See you next time.